paper, come in tomorrow morning before school, bring the paper with you, and we can do that. If you have makeup work to do, are you listening? The zeros are going to become permanent, people, if it's not made up by Thursday before school. So if you have something to get made up, you need to get it made up, all right? Some of you have stuff, we're not doing this, we're not dragging it out. If you miss something, get it figured out. You know what you missed, it's a 0 in the grade book. All right, so if there's a 40-point quest and you have a 0, that means you haven't taken it yet. And you need to get it taken because that 0 is going to become permanent. Everybody clear on that? When do we have to have it made up by? Thursday before school. That's right. Okay, and Wednesday before school is not an option because we have a faculty meeting. That's why you have late arrival. So tomorrow morning or Thursday morning, get yourself in here and get it made up. Okay? All right. Now, when I say to you sequences and series, what do you think of? You studied these a little bit last year. What do you think of when I say the word sequence or series? Oh my, no one remembers anything?
1, 2, 3,
okay,
4, 5.
Pattern. All right, so I can, so give me an example, and don't say 1, 2, 3, 4, 5. That's too basic. Give me an example of a sequence.
2, 4, 6, 8. No, 2, 4, 8.
Okay, now there's a difference between 2, 4, 6, 8, which was your first example, and 2, 4, 8, 16, which was your second example. There's a very fundamental difference between these two. They both have a pattern, right? Nobody would have an issue. Oh my, we have a visitor. Is she with you, Teresa? You want to introduce her?
This is Clem. She's from
Awesome. And you speak English?
Yes.
And you love math?
Yes.
All right. Welcome to Cathedral. All right. Now, what's going on in this first sequence? In the first sequence, how are we getting from term to term? We're adding 2. When you get from term to term by adding the same number, it is called an arithmetic sequence. Arithmetic. Now, I know when you see that word, you think arithmetic, but when we use it as an adjective, we say arithmetic. So, what is an arithmetic sequence? It is any set of numbers in which you get from term to term by adding the same number. So in this example, we are adding 2. The number that we add is called the common difference. So in this example, the common difference is 2. That's what we are adding to get from term to term. Now, will someone give me another example of another arithmetic sequence whose difference is something other than 2? Can someone give me an example of one? Okay, you guys are so creative. But yeah, that's one. 3, 6, 9, 12. There's an arithmetic sequence, and this time the difference is 3. Robert?
Do you have to start with 0 technically, or?
No, you can start with anything you want. Start with any number you want. Negative, fractions, radicals, anything. Now, what's different about this one? We're getting from term to term by multiplying by the same number. That is called a geometric sequence. A geometric sequence is a sequence of numbers in which you get from term to term by multiplying by the same number. That number that you multiply by is called the common ratio. So in this example, the ratio is, what am I multiplying by? 2. So the ratio is 2. in this example, the ratio would be, that's geometric. I'm multiplying to get from term to term. What am I multiplying by? 1/2. Now, there are formulas associated with these. Do you remember that from last year? In order, well, I'll generate one of the formulas for you, okay? And then the rest of them I'm just going to put up here so we have a little time to review. But let's come back up here for a second, and let's talk about our arithmetic sequences. Let me give you a different example. Let's try this one. All right, arithmetic or geometric? Arithmetic. Why? Because we're getting from term to term by adding 4. Okay? Now, the first term, which I'm going to use the notation a sub 1, that's the first term, is 3. Everybody agree? Now, how did I get the second term? I know it's 7, but how did I get it? I added 4. So 3 plus 4. Now, how did I get the third term? I took this one, and I added another 4. So the third term was 3 plus 2 4s. The second term was 3 plus 1 4. And the first term was 3 plus no 4s, right? So what about the fourth term? What do you think it's going to be? Look at the pattern that's developing here. It's going to be 3 plus, what do you think? 3 4s? Does that make sense to everybody? Each time, aren't I just adding another 4? So if I wanted the 12th term, using that pattern, what would the 12th term do? Now pay attention. The third term was 3 plus 2 4s. The fourth term was 3 plus 3 4s. What do you think the 12th term is going to be? 3 plus 11 4s. Isn't the number of 4s 1 less than the term number? So in general, if I wanted the nth term, it would be 3, for this sequence, it would be 3 plus what? N minus 1 4s. Would you agree with that? Now, what if I wanted to apply that idea to a different sequence? So I want to do the same thing, but not for this particular set of numbers. All right? So what was the significance of the 3? That was the first term. So I'm going to start with the first term. And then I have an n minus 1. And what was the significance of the 4? That was your common difference. Right here is your formula for the nth term, any term of any geometric sequence, or arithmetic, any arithmetic sequence. Any term of any arithmetic sequence you can find using that formula. All right, so let's do an example. Let's take another arithmetic sequence. How about 7, 2, negative 3, negative 8? All right, first of all, is that arithmetic? How am I getting from term to term? I'm adding negative 5, subtracting 5. I'm adding negative 5. So my difference is negative 5 this time. So suppose I said to you, find the 100th term of that sequence. That was arithmetic. So So what's the 100th term going to look like? The 100th term will be 7 plus 99 times negative 5. Would everybody agree with that? I just type that in on my calculator, Emma, and what do I get? I presume this is what you're typing in. Oh, what's it? Oh, anyway, that's going to be the answer. Okay? Everybody got it? Now, for geometric, there's a formula also. Remember, this is only going to apply in arithmetic situations. See that letter right there? That's your key. What does that stand for? Common difference, which is the number you add to get from term to term. So you will only use this formula in an arithmetic situation. Okay. So, what about geometric? All right, let's see. Let's think of a geometric one here. All right, first of all, is that geometric? How do you know? Getting from term to term by multiplying by 2. So your ratio is 2. All right, so let's analyze this one. See if you can come up with a pattern for this one. First term is 3. Now, how did I get the second term? 3 times 2. How did I get the next term? I took that one right there, 3 times 2, and what did I do with it? Times it by another 2. You guys following along here? So that is 3 times 2 squared. This was 3 times 2 to the first. This was 3 times 2 to the 0. Are you noticing a pattern here? What do you think the fourth term's going to be? 3 times 2 to the third. You noticing a pattern? What's the relationship between the exponent and the term number? N minus 1 again. So the nth term of this sequence would be 3 times 2 to the n minus first. So if we wanted the 10th term of this sequence, the 10th term would be 3 times 2 to the 9th. By the way, that's a pretty big number. Geometric sequences get really big really fast. How about another geometric sequence, though? What is the general formula? This works great for this set of numbers. What would it be, Brittany? Perfect. That's it right there. There is your formula. Okay? I'm going to tell you a quick story. We're going to use this formula on an actual problem. Years and years and years ago, well, you all know Mrs. Bradshaw, right, that works here? Okay, she's obviously married into the Bradshaw family, and all the Bradshaw kids went to school here. There were 5 of them. And they were all like valedictorians and salutatorians. And the oldest one, Kathy, who's an emergency room physician at St. Vincent now, I was lucky, I had her 2 years in a row for Algebra 2 and Precal. And she walked, in Algebra 2 one day, she walked in and she said, you know, Mrs. Ford, my dad and I were watching TV last night, and they said something on TV that was unbelievable. But my dad thought maybe we could figure it out in math class. And I said, all right, well, what is it? Well, they said on TV that if you put 1 checker on the first square of a checkerboard, 2 checkers on the next one, 4 on the next one, 8 on the next one, and so on. By the time you got to the last square of the checkerboard, there would be enough checkers to reach the nearest star. She said, wait a minute, the the nearest star is the sun, and it's 93 million miles away. That's ridiculous. There's no way if you start with one checker and then you go to 2 and 4 and so on, you're not going to get to 93 million. Well, let's see what you get to. How many squares are on a checkerboard? Anybody happen to know? Nobody plays chess or checkers? Oh, Lord, people, Lord. Okay, there's 64 squares on the checkerboard. All right, it's 8 by 8, it's 64. So what we would like to know, this is the first square. There's one checker on the first square, there's 2 on the second, there's 4 on the third. We want to know how many are on the 64th square. We want the 64th term of the sequence. Well, is it arithmetic or geometric? Geometric, so we're going to use this new formula right here that Brittany just gave us. So we'll start with 1. What's my ratio? 2. And I'm going to raise that to what power? Okay, let's get our calculators out. And let's take 2 to the 63rd power. Now, don't forget, when you type that in, there's a little e at the end of that number. That's your scientific notation. So this is 9.2 times 10 to the 18. All right, now, that is not a distance. That is how many checkers are on the last square. Okay, so let's think about a stack of checkers. Maybe 3 per inch. Maybe, we'll just say 3 per inch. Are you okay with that second function? So let's divide that number by 3, and that will give me the number of inches I have. Let's divide that by 12, and that will give me the number of feet I have. And then I'll divide by 5,280, and I have 4.85 times 10 to the 13th miles. The sun is 10 to the 7th away. This is almost to the sun squared. Not to the sun and back, not double that, but squared almost. Isn't that amazing? Isn't that absolutely amazing? Wow. I'll tell you one more quick story, and then I gotta get moving. This is one that I still get a kick out of it. I don't know if I should be proud of it or not, but my first year teaching, like almost everybody's first year teaching, was a total disastrous nightmare. I spent almost every day crying after school. Oh yes, it was awful. And I was blessed. Now I realize I was blessed. At the time, it did not feel like a blessing, but I now know it was a blessing. It was different then. In order to graduate, all you needed to do was pass first year algebra. That was it. That was the only required. You had to pass first year algebra. And I taught back then, now we call it college prep level. Back then we called it general. And I taught Algebra 1 general. And there were 36 of the little darlings. I was the new teacher, so I got everything dumped on me. So I had 36 of these little darlings. Most of them were freshmen. There were some sophomores. There were a couple of juniors, and there was one senior who was still trying to pass first year algebra. It was bad. There was this one kid who was absolutely wonderful, and we keep in touch. He calls me Sarge. But my deal back then was, if you were not paying attention or doing something you weren't supposed to be doing, I would have you do like push-ups or something physical like that. Well, this kid was a wrestler and very proud of his physique. And so he would actually do things wrong so that I would say to him, okay, give me 10 push-ups. He would do them one-handed, and he would just, became really a joke. He wanted to do push-ups so he could show off. So we had a woman dean at the time, like we do now, different dean, but, and so one day, I'd had it. I didn't know what to do with this kid. So I called his mom, and we set up a meeting, went down to the dean's office, and drew up a contract. And these were the terms of the contract. You have to come to school every day, because that's the law. So you're going to be in class every day. but I don't care if you do any homework. You don't have to pay attention to me. You can't disturb others, but I don't care. You can sleep. You can read something else. I don't care what you do, as long as you're not disturbing others. As long as you can keep this up. Today you're going to do 1 push-up. Tomorrow you're going to do 2. The next day you're going to do 4. The next day you're going to do 8. And we wrote this all down. And I'll never forget the dean looking at me and saying, Lisa, are you sure you want to do this? And I said, yeah. Yeah. Because what did I know that they didn't know? What's going to happen to this set of numbers? It's going to get real big, real quick. So the first week was awesome, right, for the kid. And then all of a sudden, we start getting up to numbers like 512. And after we do 512, we do 1024, 1024. Well, you know what? It all worked out in the end. But the moral of that story is, and he behaved himself, and we're still friends, like I said. He does call me Sarge. But, remember that show, Welcome Back, Kotter? Have you ever seen that show? Oh my, you need to watch it sometime, because that was my class. They were classic sweat hogs. That's what they call them in the Kotter show. They were an amazing group of kids, but oh my goodness, they were something else. And of course, I was 22 years old and thought I was going to change the world. And cried every day. So, no, it's not sad, it's character building. So the moral of that story is geometric sequences get really, really big or really, really small, depending on what your ratio is, really, really fast. Okay, that's between those two stories. Okay, now, tonight you're going to have an opportunity to practice some of those. I'm going to give you a couple more formulas. You do not have to memorize these formulas, by the way. However, you do need to know which one to use when. So far, I've given you 2 formulas. How do we know which one to use when? Whether the sequence is arithmetic or geometric. And you'll use the D formula if it's arithmetic and the R formula if it's geometric, right? Okay. Well, there comes a time when you might want to add up the terms of the sequence. Not just list them, but you might want to add them up. When we add them up, we call it a series, not a sequence. A sequence is just a list. A series is a sum when we want to add them up. Would you say this is an arithmetic series or a geometric series? This is definitely arithmetic, and we know it's arithmetic because we are getting from term to term by adding the same number. Okay? All right, one more story. This one doesn't involve me. This one happened hundreds of years ago. There was a little boy. It was a Friday afternoon, I guess before vacation. I really don't know that detail, but it was a Friday afternoon. The teacher, all boys in the classroom, 3rd or 4th grade, and the teacher was, this is true, it's a true story, it's in the encyclopedia. The teacher was kind of exasperated with them. They were antsy, everybody wanted to get going. I was going to say, okay boys, here's what I want you to do. I want you to take the numbers 1 through 100, and I want you to add them up. Now, the teacher thought the kids would do what? 1 plus 2 is 3, 3 plus 3 is 6. So an easy exercise for them, but it would take them time and keep them focused, right? So the teacher gives this assignment. All right, this is what I want you guys to do. Okay, before, the last 15 minutes or whatever, I want you to do this. Well, he no more than got sat down in his seat, and up came this little kid with the answer. And it's like, whoa, how did you do that? And I remember trying 3rd grade here. How'd you do that? And the little kid said, well, teacher, you asked me to add these up, find the sum of these. And I know that addition is commutative. So I could have added them in this order. True? Now what do you notice? If you take these two strings of numbers and add them together, you have this sum and this sum, so you have two of those sums. But what do you notice about each of these partial sums along the way? What are they all? They're all 101, aren't they? And how many of those 101s would there be in that whole long string there? 100 of them. So two of the sums are 100 101s. So what would one of the sums be? 50 101s. So there's your answer. Now, the little kid's name was Carl Friedrich Gauss, one of the greatest algebraists of all time. But his principle applies to our situation. What kind of set of numbers was he to add up? Isn't it arithmetic? So where did he get these numbers? The sum of n terms. All right, let's talk about it. Where'd that 50 come from? That 50 came from taking half of 100. And what was significant about 100? There's 100 terms. So he took the number of terms and divided it by 2. That's 100 divided by 2. Now how about 101? Where did that come from?
It's the first term.
First term plus the last term. There you go. And there's your formula for an arithmetic series. So for us, remember this was our problem? We want to add these up. How many terms do we have? We need to know that. We need to know how many we're adding up. How many are we adding up? 7. So our formula will start out with 7 over 2. Everybody okay with that? Now, what's our first term? And what's our last term? There you go. So 7 halves times 22, what is that, 77? There you go. There's the sum of the first, or of those 7 terms. Now, there's no D in this formula, so you're just going to have to remember, this is your arithmetic sum. The S kind of clues you in its sum, but you're going to have to remember it's arithmetic, okay? Any arithmetic set of numbers that you want to add up, that's the formula you're going to use. If you have a geometric set of numbers that you want to add up, let's say this set of numbers. Okay, first of all, geometric. What's going on? How am I getting from term to term? What am I doing? I'm multiplying by negative 1/2. Or if you want to think about it as dividing by negative 2, it's the same thing. Right? So it's geometric. The formula, I don't have any cool stories, sorry, you're going to write it down here. The formula for this situation is this. That is the formula that will add up the terms of a geometric sequence. Okay? So how does it work in ours? Well, let's suppose I want to find the sum of the first 10 terms. I'm going to add up 10 of them. What does the formula require me to know? I'm going to add up 10 of them. The formula requires me to know the first term, which is 6, minus 6. What did you say my ratio was? Negative 1/2. What power am I raising it to? The 10th over 1 minus negative 1/2. Now these can be a little tricky to type in on your calculator. What I suggest maybe you do is right away, you're raising this to the 10th power. What's going to happen to that negative? It's going to go away, right? And down here, this is going to become 3/2. So you might want to just take care of that before you start typing it in. When you type in the numerator, be sure you hit equals before you do divided by. Alright, so let's type it in and see if we can all get the right answer. You also might want to use decimals instead of fractions if that's easier for you. .996 is what I came up with, but I'll wait for you to confirm that. Anybody match it? All right, I've given you 4 formulas today. I hope you wrote them down. You need to know which formulas to use when. You'll get an opportunity to practice those tonight. All right, is everybody good? All right, let's get out our packet then for chapter 9. We're going to put this on hold now. We'll get back to this on, I guess it will be Friday. Keep those formulas at hand.
So is this stuff not going to be on our test?
No. This is not on the test on Thursday. The test on Thursday is over permutations, combinations, and probability. All right. I want you to find in your packet, on Friday, your homework was Precal A period 5 is the best class in the world. Okay? Back side of that. On the back side of that. Alright, so we're looking at the bus quiz. 9.1 to 9.3, bus quiz. Alright, everybody on the right page? If I do, it's in the first column over there. We handed these out a long time ago, Sarah. Yeah. Alright, here we go. How many 5-card hands from a standard deck have exactly 1 king and 3 queens? Alright, I want you to pause for a minute. How many cards do you want to have in your hand? 5. Alright, 1 of them is going to be a king. 3 of them are going to be queens. And what does that mean about the other one? It's something not a king or a queen, right? Okay, so I'm going to split my deck into 3 piles this time, because I got 3 kinds of cards in my hand. I got a king pile, a queen pile, and an everything else pile. Alright? How many queens are kings? How many kings are in the deck? 4. How many am I picking? So I will start with 4C1. Everybody in agreement? How many queens are in the deck? And I want 3 of them, so I will put 4C3. Now, how many cards are in the deck that aren't queens and aren't kings? 44. And how many of those do I want? 1. Now, why am I multiplying those together? Because I want 1 king and 3 queens and something else. Any question about that problem? Is there going to be at least 1 card problem on your test, do you think? Yes. All right, a class has 15 boys and 10 girls. 3 are selected at what is the probability of having exactly 2 boys. Now you got to pay attention. What is the probability? This is going to be a fraction. How many kids are in this class? 25. And how many of them am I picking?
3.
So your denominator is 25C3. Your denominator is the total. There are 25 kids in the class and you are picking 3 of them. Now your numerator is like this. What do you want? Well, we want exactly 2 boys. What does that mean? That means we want 2 boys and 1 girl. Remember, you're picking 3. So I want 2 boys. So that would be 15C2 and 10C1. Somebody's going to forget this. And it's going to make me mad because you need 3 kids on this team. 2 boys and 1 girl. Got it? I'm going to guess I have a 10-question multiple choice quiz. Each question has 4 options. And I'm going to randomly guess what's my probability of getting 4 correct. All right, now this problem's going to be done a little bit different than this one was. What's going on in this problem? I look at question 1 and I guess. And then I look at question 2 and I guess. And I guess and I guess 10 times, right? What do I want to have happen? I want to get 4 rights and 6 wrongs, right? Now, what is my probability of being right? 1/4. Kids, it's a 4 option A, B, C, D. What's my probability of being wrong? 3/4. Now, I want 4 of those and 6 of these. Now, what's missing here? Something is missing. I need a coefficient out here in front because does it matter which questions I get right? So I could get the first 4 right and miss everything else, or I could get right, wrong, right, wrong, right, wrong, right. There's lots of different ways I could do that. That's your coefficient. How many questions are there? 10. And how many of them do I want to get right? 4. And it's C because the order doesn't matter. Now, where else could I get that coefficient? From Pascal's triangle. Now, you have to go all the way to the 10th row. But in the 10th row, which I do not have memorized, this number would be 10 right. This number would be 9 right, 1 wrong. And you would just count your way down the line until you got to the one that said 4 right, 6 wrong. And that would be the same as this number right here. When do I use this strategy? When I am repeating, we call it an experiment, but when I'm repeating an activity over and over and over again and the probability doesn't change. Here I am guessing, 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 guessing. In how many ways can a pitcher and a catcher be chosen from a team of 9 players? What do you think? 9P2. How come it's P?
Because they're different positions.
Because they're different positions. It matters if I pick you pitcher and you catcher, or you catcher and you pitcher. It matters. 9 kids, pick 2. Order matters. In how many ways can 7 books be arranged on a shelf if 3 of the books are identical?
7.
We start with 7 factorial because there are 7 books. And when you are arranging 7 things in a line, it's 7 factorial, period. Now, what is this 3 identical? How does that play into it? Divide by 3 factorial. In how many ways can the letters of the word field trip be arranged? 1, 2, 3, 4, 5, 6, 7, 8, 9 letters all together. So it's just like the problem we just did. We start with 9 factorial. Now, do we have any duplicate letters? We have 2 I's, Do we have anything else? That it? So that's your answer. If there had been 3 p's, we would divide by a 3 factorial. Emma?
I probably have asked this before, but when we, on the test, do you want us to give you a number or you want to
Yeah,
just
no,
write
you'll
out?
work them out.
Set up? Okay.
Yeah, you'll work them out on the test. All right, number 7. There are 300 seniors. Of those, how many pre-cal students, let's say, they love neither vectors nor matrices? Losers. All right, what do you think? What's the strategy? Yep, that's gonna be a Venn diagram. I hope it feels like a Venn diagram to you. You've got overlapping sets of people. So we've got this box of people, there are 300 of them. And we've got some of them liking vectors and some of them liking matrices. Now, where do we start? When you fill in your Venn diagram, where do you start? Do you start with the 240? No, we start with the ones that love both. So this would be 70 of them right here. Oh, shoot, Judy. Okay, well, I'm gonna put your assignment on, we're gonna put it eulogy. Bring your iPads tomorrow, please. And bring this packet back, we're gonna work on it tomorrow, okay? Zach Toth.